So this is like an Ethernet, like a bus net, like a broadcast network. If H1 sends something, H2 sees it, just watching the traffic. Look at this. The traffic is sent, the report is sent to the multicast group. If H1 sends a report, H2 must get it because it has joined the group. So that's legit. It's not snooping, it's not filtering content. This is something sent to a group address. If both machines have joined that group, they should process the packet.
But what if these two are in the same subnet?
Yes.
And then they need some information from other subnets, then what?
No, it's the group address. The multicast IGMP is only, this IGMP messages are only on the subnet. They're only on the subnet. It's only between the host on the subnet and the router. Yes.
I'm wondering who sent the lead message. Is it host who sent out the report?
The last one is, one of these guys was, both have joined. One of the guys will have sent the report. If two sends the report, H1 realizes it, H1 sends the report. So everybody knows who was the last. If the last one leaves, then they send the lead message. If not the last. If H1 sends the report and it leaves the group, it sends a leave message. Kind of giving the, it doesn't say I'm the last one. It just says I couldn't be the last one. Because if I was the last one, I certainly would have sent the report. So then the router says, well, let me see if there's somebody else. It asks a query, if nobody replies, well, then that was the last one. It's completely trivial stuff, but you could not make it simpler. There's something about design where you cannot take anything away from it. Yeah, design is good if you cannot take anything away from it. And it's, in that sense, it's quite well designed. We talked about the semantics last time, and we all had a good laugh about that it's not a great model for a business concept. But the people who designed it, they were very, not kind of business. In fact, they're a very idealistic model of the internet as something that they did not have commerce in mind. Yes.
I'm just wondering, so this thing, it looks like a local, inside a subnet.
That's right.
But, in the multicast, there's a lot of times it's more of layers of, maybe like for the router one is connect to another router.
That's the routing. Very good. To keep me on schedule. That's the big part, actually. So this is only at the fringes. That's the last mile, the last hop. From the router. How does the router get the traffic? Yeah, what we're only saying is you want to get the traffic into the LAN where hosts have joined. So how does the router get the traffic? We now have to talk about building the multicast routing tree. I'm going to do that now. Alright, get the leave message. IGMP does something that is something that should have been there all the time. What IGMP version 3 has, it allows to do a source-specific joining. You're joining a multicast group for a specific sender. You're joining a multicast group for a specific sender. Now, multicast group, anybody can send to the multicast group. You don't have to be a member of the group to send to a multicast group. So, and I talked about this problem that everybody can send. If they send something accidentally, multicast to everybody. So if you're getting some real content, possibly that you're paid for, and if you join the multicast only, a multicast group, for that paid contact only for a specific sender, then nobody else can interfere with your transmission. Also for routing, much easier. So that's, if there's a big design flaw in a multicast, to not have provided this single sender multicast. It was always seen as many to many, but multicast is often one to many, one being the content provider. I don't want to have multicasting if I watch television at home, there's one sender, the content provider, sending the data down. I don't want to have anything coming from my neighbors or anybody else who's watching television. Okay, so there's something, let's see, this one here about multiple multicast routers on a network. It is interesting if you do the lab, not so interesting if you don't do it. What this has to do is, it's kind of an interesting thing. If you have multiple routers connected to a subnet, then they share their load, they coordinate. Now, what the idea of this subnet, if you're joining a multicast group, the network, then the rest of the internet, one of these routers has to then put the IP traffic in. That is called the forwarder. The forwarder is the one that passes packets from kind of this route and puts the traffic on here. Then the other one is the querier. This is the one that handles IGMP. So if you have multiple routers, you will see that they somehow agree who is the responder and who is the querier. And they do it by using IP address. Smaller IP. You change the IP address and the road changes. That's something you do in the lab. Yeah? You're doing something and change an IP address, all of a sudden they do the road change. Anyways, again, it's not fun within the lecture, yeah, because if you do it in a lab. So that's something, they're sharing the load. Yeah. Now, multicast router. So that's what has to be done. Yeah, you have to build a spanning tree. That connects, in this case here, single sender to multiple receivers, or multiple senders to multiple receivers. Turns out that building a spanning tree is not so hard. Building a good spanning tree is a little bit more difficult. So they essentially, what one has to do is solve the following problem. These are all routers. Yeah, we're done with the host. The hosts talk to their routers, so now we only talk between routers. So the hosts talk to their router using IGMP, so now we only have to talk between routers. Let's say there's the source here, and it's the router connected to the source of the sender of the multicast group. This is the network topology, and the dark green nodes, these are the nodes that have joined. So now what multicast routing has to do is build somehow a distribution tree, a routing tree that connects the source to all receivers. And it turns out there are different ways of going about this. There is the option of building a shortest path tree from the sender, the source, to all receivers. Or there's the option of building a globally optimum tree. There are two different optimization criteria. Here the question is asked, the problem that is optimized is we're trying to minimize the length of the path between each receiver and the source. This one here has path length 1, 2. There's no shorter path. This one here has 1, 2, 3. There's no shorter path than 3 hops. This one here goes in 1, 2, 1, 2, 3. You also could go 1, 2, 3 over here. There's no shorter path than that. So it builds a tree that minimizes the path cost from the source to each receiver. Do you know where all the dark rings? These are the receivers. Okay? So unicast only would have, connect a single sender to a single receiver. Multicast, we have to build a distribution tree that connects the sender to all receivers. Now, this is good if you have a single sender. If you have multiple senders, it's not really good, because you're saying if this node here becomes the sender and you're using this tree, that's a horrible tree. If this here is now the source, if you have a single routing tree, you're using this node here, so now this guy is sending, now this node is sending here in the corner, that's allowed in a multicast group, and you're using the same tree, then the path to this receiver, the minimum path is 1, but in this tree, you have 1, 2, 3, 4, you're going 4 hops. So a shortest path tree is good for a specific receiver. If you have for a specific, if you're having a single sender. If you have multiple senders, what is done is you build one tree for each sender. One tree for each sender. If you're using this solution, because otherwise the trees are just the paths that are good for this sender on top. They're bad if somebody else is a sender. Yeah? Now one thing is, these trees, these shortest path trees, they're easy to build. Yeah, because they're essentially built based on shortest path. And we know how to do shortest path. Easy to build. Okay. Easy to compute. That's just essentially shortest path. Now, second way is minimum cost tree. What's the optimization criteria here? You're trying to minimize the load on the network. What this tree here then does is it has the least number of edges. 1, 2, 3, 4, 5 edges. That means if you're sending 5 megabit per second data from the source to everybody else, then this here uses the 5 megabit per second only on 5 links. So comparing it to this one here, this is really pretty bad with respect to minimizing bandwidth use, because you're using 5 megabits per second from 1, 2, 3, 4, 5, 6, 7 links. 20% more, roughly, yeah? More bandwidth usage, more than 30%, roughly. So, a minimum cost tree turns out that building such trees is extremely, extremely difficult to do. In fact, if you have a network with 40 nodes, 30 nodes, you could still do it on a computer cluster if you had a few days. You need maybe 100 computers, let them run, but they can do it. For 40, there may be a few computers that still can compute it. 50 can forget about it. It's related to a problem. If you have worked on routing path on chips, a routing problem on chips has a similar problem, where you're essentially trying to minimize the amount of cables that you have, and you have multiple attachment points. It's related to it. This is an algorithmic problem known as the Steiner tree problem. Steiner tree. It's a famous. It's a very, very hard problem, and it can essentially only solve approximately. So what we find, but what is good about this is once you build the tree, this tree is good for all senders. You can reuse the tree. So in routing, this is sometimes the multicast routing is called as a shared tree. Shared tree. Okay. So turns out in multicast routing, both approaches are found. The shortest path tree is used, and the shared tree is being used, but not in terms of this optimal solution. It's the minimum cost tree. This one is not built. It is built, and it tries to build an approximation of this in a very simple way. So, first, the source-based tree is essentially the problem of minimizing the path from each receiver to the sender. It builds one shortest path tree for each sender. Separate tree built for each sender. If you're having different senders, different tree has to be built. Yes?
So all routers on the way should remember all this pattern tree?
Absolutely.
So doesn't that like grow with the size of the host?
Look at it. The routing table entry. You're having a routing table entry for a group. You're having multiple trees. You're having a different routing table entry if you have a new sender to the group. You're having one routing table entry not only for each group, but even for each sender in the group, because it's a different tree. Absolutely, that's bad. Bad for scalability and routing. Look at this. I mean, you're starting to send to a group, all of a sudden, routing table change. Yeah, that's the thing with a tree. Yeah, it sounds pretty easy algorithmically, but yes. It's as bad. The tree is built from the receiver to the sender. And it's using this concept called reverse shortest path and reverse path forwarding, which I explained. I just want to show that the key element for, if it gets to the business of building the route, is all based on reverse path forwarding. You're building the route from the receiver towards the opponent. In this case here, towards the source, sender in the group. The second tree version is kind of an attempt to solve this, to do something like this, build a single tree that can be shared by all senders and receivers. This one is not possible. It doesn't even try. Yeah? But it builds a single distribution tree that is shared by all senders. So it does not use solution 2 because it cannot be done. What it does, kind of a very simple solution, it just says, okay, let's pick a node in the center of the network. We call that the core. We put that in the middle. We put this node over here, the second, the one below the source, it's pretty much in the center, yeah, of all these nodes, either this one or this one. Let's take this one here, the one below the source. Then everybody builds the shortest path to that center node. This node that is being picked is called the core. So these approaches are called core-based trees. You have to determine a core, and you route towards it. Everybody routes towards the core. So you're getting a pretty decent tree. The question, of course, is who picks the core? How do you know that the core is well picked? Well, frankly, there's no solution to that. But these core-based trees do exist in the main multicast protocol, even if they exist only for a short time. Then you select one router as the core or rendezvous point. There's a routing protocol that calls it rendezvous point. That's where you run. Let's call it core here for the time being. And then everybody builds a shortest path to the core using reverse path forwarding. Yeah, so this concept of reverse shortest path and reverse path forwarding, that's so let's discuss it. Let's see, one more thing. Yes, before we do that, the issue with the routing tables. Routing table entries have a multicast group. This is the multicast group effect. And then they have an outgoing interface list. That's where the bifurcation happens. They also have an incoming interface list. That is the RPF, reverse path forwarding interface. I will say how this gets done. And what you have is, if you're building source-specific trees, there's also the source IP address. So if you're building source-specific trees, the routing table entry is source and group. Source-based trees with source group here. If you're getting something from a source, from this source, for this group, where traffic arrives on this interface, send it out and these two interfaces. For shared trees, you don't have, you only have one routing table entry for each group. So these are called star G entries. Star G means for all senders, there's one entry. If you're getting data on interface, you send it out on the All right, now on reverse shortest path. So it's essentially, what you're trying to do is you're trying to build a shortest path. And normally what you would try to do is you would try to build the shortest path from the receiver to the sender. Or what you're trying to do now, you're trying to build the shortest path from the sender to the receiver. From the sender to the receiver. Yeah, that's the shortest path you're trying to build. Now, the way that what reverse path forwarding does, it takes advantage of the fact that shortest path is already computed by the shortest route, by the routing table. The routing table has already computed via OSPF or via REP, probably via OSPF, the shortest path between all nodes. So each router has each router has, for each destination in the network, already a next hop, which computes the shortest path. Let's look at this example. We are focused on a decision of the routing table at router R3. Now, we're looking at a multicast group where the sender is from the source of H1. Now, H1 is the source for multicasting, the sender for multicasting. Now, router 3 has for this address, now this of course is the network address of this router, for this network address, it has a next hop. So if router R3 would have a packet, would send a packet to H1, it would send it to this router R2. Yeah, that's its routing table. This has nothing special. So of all its neighbors, 1, 2, 4, and 5, R3 would pick R2. Now, the way this is now happening is that multicast traffic, the routing table entry for multicasting from host 1 will be going on the reverse path, that will be going on the hop that is the reverse path interface for that source. Router 3 to host 1 will send it to R2. This will set this interface to R2 as the reverse path interface for host 1. Which makes the next router, R2, as the RTF neighbor of router 3 for host 1. RTF interface, unicast routing determines the RTF interface. The next hop on that RTF interface, that is the RTF neighbor. So now what multicast routing does is that H3 will now enforce a routing table entry on router 2 for forwarding multicast data that is coming from H1. That's the reverse portion. Router R2 will then look, what is my shortest path to get to H1? It will have an RTF neighbor. Then router 2 will tell its neighbor, please set your routing table for this particular multicast group with sender H1 to my interface. So what's happening is that the routing table, the routing path is sent coming from the bottom of the tree is built towards the source. And if it's a core-based tree, towards the core. You just replace the source with a core. Everybody builds a tree towards the core. That's clever.
What do you mean by the core?
The core is, there were these two groups of multicast routing algorithms. There was this per sender shortest path tree, that's the group 1. Number 2 is where you're picking a node in the middle. That's the core, the center of the tree. Everybody builds a route towards that center, then you're having a single tree that can be shared by all senders. So what you need to then do is you need to then, kind of the routing table is not built from the core to all through the network. No, it's built from a router towards the core. And the shortest path is then, the data is then not traveling the shortest path from the core to the receivers or from the source to the receivers. It's traveling a path that if it was traversed the reverse direction would be the shortest path. Well, packet RPF40. For the packet, only if it's received from an RPF neighbor. Let's talk about it. Yes, this comes with the reverse shortest path, the union of reverse shortest path with the reverse shortest path tree. Let's maybe do a simple example. Let's see. Let's try to build a source-based tree. So what we have here is a network with 8 routers, R1, 2, 3, 4, 5, 6, 7, 8. Then we have 1, 2, 3, 4, 5 Ethernet network. And each Ethernet network is a group. There is one sender, H1, and 2 hosts on these networks here have joined the group. What does it mean? The groups here, H4 has sent an RGMP packet to R7. So R7 knows it should put something, it should get the data for this group and put it on the network. The same for H3. These guys here don't have a joint memory. So what is now happening? Yeah, so what's now happening in the beginning? Yeah, no tree is built. What's happening is initially data is flooded in the network. Okay, data is flooded. Flooding means everybody sends the data. You're receiving a multicast group from H1, the source. You send it out on all interfaces. Let's look at router 2. It gets the packet from R1. Or let's say it's R1 gets the packet from H1, puts it out on all interfaces. R2 gets the packet from R1, puts it out on all interfaces. R4 gets the packet from R2, puts it out on R5, R3, R7. Everybody receives multiple copies. But the data is coming from H1. So everybody, each router knows if it sends traffic to H1, it would know how it goes. And let's suppose the unicast routing is like this. Unicast routing is like this, so if R4 sends the packet to H1, it would send the packet to R2. If R7 sends a packet to H1, it would pick R3 at its next hop. So the link up is the reverse path, indicates the reverse path neighbor with respect to H1. So now something's happening. So everybody knows this. R7 knows that R3 is the RPF neighbor. Is the RPF neighbor with respect to H1. The red part is indicated by units obtained from unicast routing. So now what the routers do is, for each packet that is received, if it is received from a non-RPF neighbor, it throws the packet away. And not only that, it throws the packet away, and if it does this, it sends a message back saying, don't send them. Stop sending. It's called a prune. It prunes the tree. Flooding, I know where I want to have the data from H1 Pro. I get it from different interfaces. I tell them, don't send it to me. Which prunes the tree. So all of these X's indicating here, this is where data is received on a non-RPF interface. Then they send the prune message, and what is left over is the data that has been forwarded on the reverse. What is left over is the data that is forwarded along the reverse shortest path tree. So the tree is not built, it is pruned. Very interesting. That's what is left over. Couple of things. So send a prune message when the packet is received on a non-RPF interface and when there's no receiver downstream. Prune message disables routing table entry. It disables it, but only temporarily. For a period of time. Soft state. a prune message has to be repeated every so often. If no prune message is received, well, it's being forwarded again. So that's how this works. So this is essentially so this flood and prune algorithm is essentially the first group of multicast protocols. This is called, do I have it here? DVMRP. DVMRP, the first one here. Yeah? It's the first multicast routing protocol designed in the early 1990s. It assumes, let's see, it implements flood and prune. The overlay thing, I have to go that separately. Yeah. So that's essentially flood and prune, but you see it's very, this flooding, periodic flooding of data, it's not such a great idea. So people have continued to work on it. The core base tree is, didn't really quite make it. Also was in the early 90s. That essentially introduced the concept of a shared tree. The routing protocol for multicasting that I use is essentially PIM, Protocol Independent Multicast, which exists in two versions, where one version is flood and prune, and the other version is requires it uses a rendezvous point, and that mix of two things. We have maybe time to discuss it tomorrow. But what I'm going to do is tomorrow I'll just start exam preparation, yeah? And if we have some time, we can still cover some of multi.
So the exam was setting up to here for the IP multicast?
Yeah, but I'll be careful about not having, I have in mind that this new material. So if something comes here, it will be something more or less from the lecture. Or from the write-up. Yeah, but which is essentially the same. All right.